All right, moving on to unit 3, we're talking about rational functions. Now, rational functions are just polynomials divided by polynomials. So some rational function is just going to be some polynomial divided by some polynomial. Now, here's the key. In unit 2, we discovered that zeros of polynomials are very important. Well, zeros of the polynomials in the top and in the bottom are very important, because we're going to have many situations with how we could have zeros in this fraction form. One option is you have a 0 divided by something that's not 0. Well, 0 divided by anything is 0. So if you ever have a 0 on the top and there's not a 0 on the bottom, this would be a location of an x-intercept. Another option is we could have a number divided by 0, so we have a 0 in a denominator. Now, we'll talk about this when we see it more. This is an indication that we have a vertical asymptote. The reasoning why is because we'll end up, as we get close to that number, with 0 divided by a number divided by something very close to 0. If you think about something divided by something very, very, very small, it's going to be very, very, very large. So this is the reasoning why vertical asymptotes occur when you have a number over 0. And then the final thing that we will discover is a 0 divided by 0. And we'll talk about it more. That's an indication that you have a hole in your graph. Now, why do you have a hole? Well, let's think about if we have some sort of number times 0 over 0 times another number. If we have a situation when this occurs, we would love to be able to just like cancel out the factors, and then we'd be left with the numbers. Now, we're not allowed to. Zeros divided by 0 is undefined, so we don't have a point there. However, again, just like what we talked about with the vertical asymptotes, as we get close to that location, we will get something close to 0, which we can cancel. We could see we'd be approaching some sort of like fraction, some sort of number. And that's why we have a hole at that location. All right, so that's the keys to rational functions, and I'm sure there's more into it, and there's limit notation of all of these things that we could talk about. So let's just get into it. End behavior is the first thing. Now, we didn't talk about end behavior, but if for polynomials, we care about the biggest degree term, for rational functions, we're going to care about the biggest degree terms in the numerator and the denominator. We have to be comfortable with limit notation for end behavior. Means we're looking all the way to the right or all the way to the left. Now, if I only care about 2x over x squared, you can either think about this as a series of fractions that are slower over faster. Think about a series of fractions where the numerator grows slower than the denominator. What's happening to each subsequent fraction? It's getting closer to 0. Or after simplifying this and thinking about plugging in infinity, you can think about 2 divided by infinity approaching 0. So as our input values increase with outbound, our output values are getting close to 0. Okay, another end behavior statement, but we are decreasing with outbound. So again, we break out our limit, think about plugging large negative values. If we are decreasing with outbound, we are going to the left towards negative infinity. I only care about the highest degree terms. Now, what happens? Well, here, the growth of this x squared and the growth of this x squared is going to cancel. We'll have like 4, we'll have 8, and this is 1 over 1. We'll have 4, we'll have 8, this is 10 over 10. Doesn't matter. These things are going to grow at the same rate. Since they are growing at the same rate, the growth is going to be canceling, and it's just going to leave you with these leading coefficients. I'm not memorizing how to do these problems. I'm understanding them, and that's how I'm getting my answers. Another end behavior. Looks like we're plugging in negative infinity again. We have the fastest growing terms that we care about. We're going to be careful. Maybe it's best to simplify to realize the end behavior of this rational function will be the same as the end behavior of this polynomial, this y equals x. You could also think about plugging in values. It's going to be faster over slower. However, the denominator is always going to be a negative value, meaning our subsequent fractions are going to get bigger if the numerator is growing faster than the denominator, but it'll be bigger in the negative direction. It'll be larger negative values. So that's one way. Here's the other way. Y equals x. What's the end behavior? Like that. If I go towards negative infinity, I get y's of negative infinity. And that's really what it's saying. It has the same end behavior as y equals x. I didn't really see that. Okay, but what's the difference between these two statements? Since the polynomial numerator dominates the polynomial denominator, like this is the exact way as I understand things. Yes, numerator dominates the denominator, not dominator dominates the numerator. So, okay. Just like with polynomials, zeros are important, but with rational functions, zeros everywhere are important. Zeros at the top, which will be the location of a zero. Zeros at the bottom, which are locations of vertical asymptotes, are important. We only care about the signs when things are positive. The same kind of idea about multiplicity and signs changing follows. The multiplicities of these roots are 1. Plug in a test point like 4 or 5, we get positives. We see the multiplicity of 3 is 1, so we will change signs. We see the multiplicity at -2 is 1, so we will change signs. We should understand, and we can do a little bit more analysis around how we are going to be trending towards negative infinity around this vertical asymptote, how we're going to be coming from infinity. If we need to talk about a limit statement soon about to the left and right of 3, we could talk about that. But right now we're just talking about when are we positive. And here we are positive, and here we are positive. To the left of -2 and to the right of 3. Okay. Zeros. 0 over a number. If you ever get 0 over 0, whole. If you ever get a number over 0, vertical asymptote. We have a 0 at -3 and 4. That means we need -3 and 4 to have a 0 in the top. Okay. We got that. We got that. We got that. We don't have, immediately we can cross that out. So, and this one, because if I plug in -3, I should get 0. So it's in between these two. Now, let's see if there's an obvious one that we can go away from. Here we go. If I plug in -3, I'd get a 0 in the top, I'd get a number in the bottom. Checks out. If I plug in 4, I'd get a 0 in the top because of that, but I'd get a number in the bottom. That checks out. Okay. The problem with 4 here is we'd have a 0 over a 0. Now, careful with the amounts of zeros. Here I have like 0 to the 3rd power versus 0 squared, which means it would simplify to be 0. Here, x equals 4, which is a 0 over 0, is the location of a whole. The whole happens to be located at y equals 0. Look at wholes more in a second. If this was the other way around, if it was like 0 squared over 0 cubed, then you'd end up with like 1 over 0. And that's an indication that we have a vertical asymptote. Anyways, this one was pretty easy because we just want 0 over a number. All right. Now we're talking about vertical asymptotes. We saw at x equals -3, we'll have a 0 in the bottom but a number in the top, we have a vertical asymptote. We can see at 2, we'd have a 0 at the top. Now, multiple ways to do this. You can either do a full sign analysis, or you just do a smaller sign analysis, like around -3. Let's do the full sign analysis and the small sign analysis. Let's get the same answer. If I plugged in a test point like 3, positive, positive, positive. Multiplicity is 1, multiplicity is 1. Okay, cool. This shows me that I'm trending towards positive infinity to the left of -3. I'm going to be coming from negative infinity to the right of -3. One way to do it. You can get your answer from there. Other way, plug in a value that's very, very close to -3 to the left and to the right. If I plug in -2.999, the top would be negative. The bottom would be a positive value very, very close to 0, which is why I have these very, very large negative values. If I plug in -3.001, I'd have that negative value on the top. The bottom would be a very, very small value close to 0, but that's negative. Negative divided by a negative is a positive. So we're trending towards positive infinity. A number divided by something infinitely small is infinitely large. So let's pay attention. To the right of -3, to the right of -3, I'm trending towards negative infinity. To the right of -3, to the right of -3, I'm trending towards negative infinity. Don't go to the right that way. We are looking just to the right. This is a big mistake. A lot of students, when they see this plus, think moving that way. It's like, no. It's actually getting closer to -3 from the right. So this is why my answer is negative infinity. Okay, same deal. We're focusing our attention at -4. So we understand that at -4, we do have a vertical asymptote because we'll have a 0 in the bottom. You can see at 6 we have a 0. You can do a full sign analysis or just a smaller sign analysis. I think the full sign analysis is probably easier here. If I plug in something like 7, we got a positive. We will change signs. We won't change signs because this multiplicity is 2. The degree of that is 2. Squaring numbers in the bottom will always make them positive, which means the sign won't change to the left and right of -4. So right now I can get my answer. Knowing that that's a vertical asymptote, I can see to the left, approaching -4 from the left, approaching -4 from the right. We're both trending towards negative infinity watts. If we wanted to use the smaller sign analysis, you could plug in -3.999. You could plug in -4.001. You plug in -3.999 minus 6, that's going to be a negative value. I don't really care exactly what it is because I know it's a number that's negative. If I plug in -3.9999, add 4, it's close to 0, and positive squared stays positive. So we have a number that's close to 0, positive. That's why I know we have these negative large values. On the other side of things, -4 minus 6, still negative number. -4.001 plus 4 is going to be a very small negative number, but squared makes it a very small positive number. Again, there's that sign's not changing. So since we're squaring, this sign is always going to be positive. We have this negative, so that's another way to get that. Really, you're looking for negative infinity in both directions, approaching -4 from the left, -4 from the right. I would say like the full sign analysis is probably quicker to do and less prone to mistakes. Okay, now we're talking about getting close to 2. All right. If I'm getting close to 2, what would happen? Now here's the hole. Here is the hole. If I plugged in 2, I'd get 0/0. Now, sometimes it's good to just like plug in values close to, like here I plugged in -4.001, -3.999. We could think about doing that, but it confuses a lot of students. Let's just plug in 2, and then I'll tell you like what we're actually doing. If I plug in 2, I get negative 2 times 3 times 0, and then 0 times 12. Homework?
Yes.
Yeah. Just try to complete as much as possible. The whole packet's done by Thursday. Okay? Now, 0 over 0 is an indication that we have a whole. You're not allowed to divide by 0, even if it's 0 over 0. However, if we could cancel these zeros, what would we be left with? Homework? Grab it. Try to complete as much as you can. Entire packet's done by Thursday. Yep. We can see if the zeros canceled, we'd be left with this negative 6/12, which is negative 1/2. The idea behind this is that you're not really plugging in 2. You're plugging in values close to 2. If you plug in values close to 2, you're going to get a value very, very close to 3. You're going to get a value very, very close to 0, a value very, very, very close to 0, and a value very, very close to 12. Now, these numbers can cancel, they do disappear. It shows that we are approaching a very specific y coordinate. But what's like 3 point, like, don't worry about it. Just pretend it's like it's arbitrarily close to 3. It's 3. That's another way, and that's the idea behind how wholes have locations. They have y coordinate locations, and that's where we are. Okay, whole 0 over 0. Make sure we have the same amount of zeros or more zeros on the top than the bottom. If we have more zeros on the bottom than the top, it's a vertical asymptote. So this is 0 over 0 squared. That's going to simplify to be 1 over 0. That's the location of a vertical asymptote. This doesn't have a hole. This is a 0. Here, vertical asymptote. Here, we'd end up with 0 squared over 0, which simplifies to be 0. This would be a hole at y equals 0, or at the point 0, 0. There wouldn't be a point, there'd be a hole. I don't think they're going to worry too much about these multiplicities. I think it was a big thing with Mr. Passwater. Good job, Mr. Passwater. Shout out. However, I think they're going to keep it a little bit more simple. But we'll see. Okay, what is the domain? What are the x's that we can plug in? Well, we can't plug in x's so that we get an undefined value. We're allowed to have zeros in the top, provided we don't have the same zeros in the bottom. I can't have 1. You're probably thinking, well, doesn't this x minus 1 cancel? No, don't cancel things. If I plugged in 1, you'd get 0 over 0. 0 over 0 is an indication that you have a hole. This rational function has a hole at x equals 1. The hole happens to be located at 0, but it's a hole regardless. Because it's like 0 squared over 0, it will cancel and just give you 0. It's still a hole. You're not allowed to divide by 0 ever. You're not allowed to plug in negative 3 because you'd have a 0 in the denominator. You won't have a 0 in the numerator. You get something like that. That's an indication of a vertical asymptote. You are allowed to plug in negative 2. If you plug in negative 2, that's a 0. A 0 is a point. It is an x-intercept. That's fine. So it's just 1 and negative 3. Okay. X equals 4. 0 over 0. 2 zeros on the top, 1 0 on the bottom. We'd end up with 0, but it's still a hole. It's just the hole is located at 0. X equals 2, vertical asymptote. Same with this. This is like, he's really going hard on these multiplicities. X equals negative 2. We get 0 squared over 0. Well, we'd end up with 0, not number over 0, x equals -2 whole. X equals 3. This kind of like is the perfect example showing you. X equals 3, you'd end up with 0 squared over 0 cubed, which will simplify to be like 1 over 0 after you cancel 2 of these zeros and 2s. That's an indication of a vertical asymptote. If you ever end up after simplifying with a number over 0, the zeros on the bottom are more than the zeros on the top. So 3 is a vertical asymptote. -2 is a whole. We don't have a 0. We don't have 0 over a number. Okay, x equals -4. We need to get 0 over number. X equals 3. We should get a number over 0. X equals -4, 0 over a number. X equals 3. We'd have 7 times 0 over 0 squared. It would end up being a number over 0 at x equals 3. D. Oh, word! What happens if you have something like this over something like this? Could we be a little bit more specific about our end behavior? You can probably understand that if I'm plugging in big numbers, I don't care about this, this, and this. You'd be like, oh, the end behavior is the same as 3x. But could we be a little bit more specific? Is it just 3x? Well, one way to help us see more specifically what this rational function is doing is by dividing the rational function and giving its equivalent form as just a sum of a bunch of things. Okay. And I really like teaching this because you can see the equivalent stuff. We're going to divide. Now, there's two ways to divide. You can either use long division. Some of you love it. Or if we want to do a shortcut, we can use synthetic division. Now, synthetic division is just long division. Instead of subtracting, we add. But to be able to add instead of subtract, instead of worrying about x plus 5, we worry about x we worry about the root. We like change that value of 5 to -5. I'm going to show both ways. It's just like dividing numbers into numbers. Like what's the thing could get rid of this one? It's like 3x would get rid of this. We multiply them together. We get 3x squared plus 15x. We then subtract. When we subtract, we get that. We bring down the next number. We then have that times that, which will give us this. When we subtract, add the opposite, we get this remainder of 40, which means 3x squared plus 9x plus 10 divided by x plus 5 is actually equivalent to 3x minus 6 plus the remainder of 40 x plus 5s. Here, you get the same result. Multiply, add, multiply. Remainder, numbers, x's. Okay, I got to show this on Desmos because it's so much fun. It's your call. It's your call. What's your first period? Yes. Okay, watch. Love it. Love this. Y equals 3x squared plus 9x plus 10 divided by x plus 5. Okay, here is my rational function. Cool. I'm missing the other half of it. There it is. Okay, cool. All right. we can see it has very similar end behavior to y equals 3x in terms of going in the same direction as this rational function there. But we can see more specifically that 3x minus 6 is dead on with this rational function's end behavior. We can see if that we add the remainder, we have the exact same function. We just rewrote it in its equivalent form as a fraction divided together. So we can see this is equivalent to this. However, if we are plugging in infinity, this is going to go to 0, and really you just care about 3x minus 6, which will have the exact same end behavior as this rational function. 3x was close. 3x gives you the general direction. 3x minus 6 is exactly how this rational function's end behavior is going to look, which I love showing. I don't want to pause my video. So there, great. Didn't answer the question though. The question was, what's the remainder? So slope of the slant asymptote. I mean, I kind of know the answer just by keeping this simple. The slope is going to be 1. If you take x cubed and divide it by x squared, you're going to get x, not 3x. Just the leading coefficients, like the biggest degree terms, are really all I care about. Like, I know it's 1. If you want to be sure, you can divide. But, like, you don't have to do all of the work that I just did. You know this has to be x to get x cubed plus 3x squared. Subtract negative x squared minus 6x. You could keep going if you wanted the specific slant asymptote or the linear equation of the same end behavior. But it's just the slope of the slant asymptote. What's going on here? Careful, don't cross this out. Don't be like, oh, that doesn't matter. This is really like x cubed plus stuff minus x cubed. The x cubes will cancel. They're gone, which means the next highest degree of stuff would be like the dominating thing. And that's a great question. This is a great question, Mr. Passwater. We got to figure out how many x squareds do we have. Now you can either take x minus 2 cubed, or hey, let's just practice our binomial theorem. Remember Pascal's triangle? These end up the coefficients of a plus b. This is a plus b to the 0. This is a plus b to the first. This is 1a plus 1b. This is a plus b squared. This is 1a squared, 2ab, 1b squared. These are the coefficients of 1ab cubed. We'll have 1a cubed, 3a squared b's, where you kind of bring one down and raise the other powers of the other one. We have 3ab squared, and we have 1b cubed. So we have x squareds. We'll have 3 x squareds times b, which will be negative 6x squared. Or just do the math and multiply things out. Let's square x minus 2 and then multiply by another x minus 2. We get x squared minus 4x plus 4 times x minus 2. I'd have an x cubed. I have negative 2x squareds, and then positive 8x squared, which is negative 4x squared, negative 2x squared, negative 6x squared, just like I suspected. We'd have 8x's and 4x's, which are 12x's. This is 3 times a times b squared. That's 3 times x times negative 2 squared. Boom, there's 12x. Then we have negative 8. That's negative 2 cubed. So anyways, the x cubes do go away. you are left with negative 6x squared as the dominating term in the numerator, positive 3x squareds in the denominator. Negative 2 would be our end behavior. Horizontal asymptotes. What's a horizontal asymptote? It refers to our end behavior. If we get a number, that's a horizontal asymptote. If we don't get a number, we'll be trending towards infinity. We'll have a slant asymptote potentially, or we'll have the end behavior of whatever polynomial ends up. Okay, that's unit 3. It's a good unit. A lot of people forget all about rational functions, and it was one of the tougher units from the year.